Okay, we already talked about one optimization problem in 4.7, example number 1a. And before we get into the next example, I want to talk real quick about a few steps that we should be following anytime we're trying to do an optimization problem, trying to find the best way of doing something. So the first thing that we should always be doing is writing an equation that we're trying to optimize. So we need to think about what we're trying to find the maximum or minimum of. Are we trying to find the maximum product? Are we trying to find the maximum area? Are we trying to find the least expensive item? Whatever it might be, okay? So come up with an equation that you're trying to find the maximum or minimum of. But sometimes that equation has multiple variables in it, and there's too many changing pieces to figure everything out. And so then the second step is we might need to use a secondary equation to help us rewrite it with a single variable. So is there something else that we know about the situation that we can take one variable and write it in terms of the other? We can then substitute that into the optimization equation, the one that we're trying to find the maximum of, so that we can find the actual maximum or minimum, where we take the derivative, we find those critical numbers where it equals 0 or does not exist, and we can use those then critical numbers to figure out if we have a relative extrema, okay? But we also have to make sure that the answers make sense. So we need to determine the reasonableness of our solution. Oftentimes we find a relative minimum, but maybe that's not the absolute best value. Maybe it's just a relative maximum or a relative minimum. So we need to also discuss what our domain restrictions are. What's the lowest, what's the highest it could possibly be, and possibly test those endpoints, because those could be better than the relative extrema. Let's do another quick example in this video, example number 1b. It says here a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So we know that we're trying to find the largest, the maximum area. So step number 1 is thinking of an equation that we're trying to optimize, find the maximum of. And so in this problem, it asks us to find the maximum area. And so I drew a little picture of my rectangle, and I know that I want to find the maximum area of this rectangle, and I know that area is really length times width. The problem is there's lots of different variables in there, and we can find the rate at which the area changes, but the length is going to change and the width is going to change, and that's a lot of changing pieces, too many variables. So what we have to do is think of something else that we know about this situation, a secondary equation that might have L's and W's in it, so that we can solve it for one variable or the other. And so what else do we know about this scenario? Well, doesn't it tell us that we have 24 feet of fencing? And so that means we can go along the width, we can go along the length, we can go around the second width. Remember, there's no fence needed along the river. So that means we have 2 L's and 2 W's and 1 L, right? 2 widths and 1 length for a total of 2,400 feet. So then I should be able to take that equation, I should be able to solve it for one variable or the other, and it shouldn't matter which one. In this case, I just solved it for L because it was a little bit easier. And then we can take that and plug it into the formula that we're actually trying to, the equation we're actually trying to optimize. So instead of saying length times width, I'm now going to say that it's really 2,400 minus 2W, which is really the same thing as my length from my previous equation, times my width. I'm then going to simplify it a little bit by distributing the W through. I get a new area equation that says 2,400W minus 2W squared. So this is my original area function that I'm trying to find the maximum of. I want to figure out when the derivative goes from positive to negative. Before I can do that, we've got to find our derivative, we've got to find our critical numbers, and we have to make sure that we actually found a maximum and not accidentally a minimum. So now we need to take this equation, we need to find the derivative. I ended up getting a derivative of 2,400 minus 4W. The rate at which the area changes with respect to that width changing is 2,400 minus 4W. I'm going to find my critical numbers now by setting that derivative equal to 0 or do not exist. I'm going to solve, and I end up getting a critical number of W equals 600. Remember, W meant the width of our fencing. And so I'm thinking that I might have a possible maximum, or though maybe a minimum, when w equals 600, because can't my derivative equal 0 at a minimum or a maximum? And so really we should be testing to make sure that we found what we're looking for, a maximum, and not the opposite, a minimum. And so doing my sign chart, I can go over here and figure out what the derivative value is, just less than 600 and then just greater than 600. So I can plug in a number that is less than 600, a number that's greater than 600 in my derivative to see if my derivative is positive or negative. Try some numbers. Try 500, try 700, and see what you get. I ended up getting that my derivative changes from positive to negative. If that's the case, and my derivative changes from positive to negative, then I know that my original area is increasing and then decreasing. So it looks like 600 is a relative minimum, which is a pretty good answer, but is that the best answer we could possibly come up with? Is that the absolute maximum value? And before we can do that, we've got to figure out what our endpoints are, because remember, in order to find our absolute maximum, we need to not only plug in our critical numbers, we also have to plug in our endpoints to see if they're higher or lower. So what we have to do is think about our domain. We've got to think about what w is the lowest we could possibly have and what w is the highest we could possibly have, so we can test our endpoints. And I'm talking about w because that's what we solved for in our problem. If we did and solve for L, then we would have to discuss what the maximum length would be. And so what's the lowest the width could ever possibly be? Well, to me, the lowest it could ever be is 0, right? Now, if the width is 0, then I would have no area for my, whatever this is, field. But that is technically the lowest it could go. What's the highest width could be, though? Well, we got to be careful. If I know that there is a restriction that 2w plus 1l equals 24, well, if the length is 0 and we use everything for the width, and then I have 2 of them and I have to divide it in half, well then really the maximum that my width could be is 1200. If I only have 2400 feet of fence and there's 2 widths, well the maximum it could be is 1200 feet each. So really my domain is anywhere from 0 to 1200. Really those are my endpoints then. So if I'm double checking to make sure that I have an absolute maximum, remember I'm taking that critical number and I'm taking the 2 endpoints and I'm plugging them into my original area equation because I want to see what one's going to give me the best area. If you plug in 0 though to that area equation, don't you end up getting 0? And that should make sense. If your width is 0 and you squish this down, well then you don't have any area. Your area should be 0. And if you plug in 1200 to your area, what ends up happening? Don't you also end up getting 0? Because if the 2 widths are 1200 feet each, you've just used up all your fence on the 2 widths, which means you've squished your area and there is no length, and so you have no area again. And so a lot of times when we test for absolute extrema and we're talking about an area problem, it ends up kind of squishing the other dimension and you end up zeroing out the area. So testing the endpoints don't actually give me a better value. When I plug in 600 though, I ended up getting an area of 720,000 square feet. That's a pretty darn big area. And so if that's what I'm looking for, then I know that the width has to be 600. I know that the area then is going to be 720,000 square feet, which is the maximum area possible. But the question also asks me for both dimensions, not just the width, but also the length. Well, now that I know that the width has to be 600, I should be able to plug that in. I should be able to plug that in up here to figure out what the length is. And so if the width is 600, then I can tell, that the length is going to be 1200 feet. So as long as my width is 600, as long as my length is 1200, I end up getting a maximum possible area for my rectangle of 720,000 square feet.